Hey, what's up, guys? Yeah, I just got sick. So yeah. Okay, so today a very short video. Probably not too short. Basically, this is interesting. I find that there is a way to like transfer this plate shorts PDE right into heat equation. So I think this is a way that people solve this PDE. So basically using after transform to heat equation, then you can use a further analysis, or basically there's a so-called kernel method, or basically the Green's function. There's a many way in the like engineering mathematics or mathematical physics that uh one can solve this equation once you translate your PDE into the heat equation. So in this video, that our goal is to make this connection clearly. Make this connection clearly. This is interesting. Okay. Very tedious but interesting. Okay. So let's write the equation like this. Okay, so the derivation of this equation need to use the stochastic calculus. So skip. You can check out my previous video. So basically you have like basically you have this differential equation on T and on S. So ST, right? And then there's a SSV. Okay, so you can, so everything you see, every time you see this S square and SS, and this remind there's a probably not remind you, but remind me that there's a in a ODE, right? There's a cos ODE, right? So there's a this kind of equation. Okay, so how to solve this kind of equation? So the standard technique is to translate to translate your variable, right? To translate your variable to take exponential. Okay. So in this way that since we want to ignore this x squared, right? So that means that we need to change the variable on this s. Okay. Okay. So this gives us the first hint. Okay. So the first step and the second step is translate this t. So it's very simple. So let's make the change of variable. So the change of variable, that s to be exponential x, and small t equals to capital T minus 2 divided by minus 2 tau divided by sigma squared. And there is a boundary condition that you need to also change it, but let's first skip this. Okay, so now you have these two, so we can like make a fun game, right? So we can write partial v partial t into by the way, tau, and we need to change by the way, this capital T is constant. Okay. So partial v partial t will be just this, right? So it's linear in tau, right? So just this t just a scale of this tau, right? So it's basically minus sigma squared divided by 2 partial v partial tau. Okay, this is simple. And so these two are basically still there's no correlation between two. Okay, so it's partial v partial s, right? So it's basically simple, right? Partial v partial x partial s. So but s is exponential x, right? So it's ds equals to s dx, right? So your partial x partial s will be 1 over s. Okay, and your partial v squared partial s squared, very standard technique. Basically, it's 1 minus s squared partial v partial x, and now we use the chain rule again, right? We use a s squared. We use a partial s partial v partial x. Use the same trick again, right? So we change it 1 over s partial v partial x square. Okay, so it's square. Okay, so this is what we need to know. Ooh. Let's see. Okay. Okay, so the first one, that partial v partial t become this partial v partial tau, and plus plus the half of sigma square s squared. So it's half of sigma squared, and s squared is -1 s squared, right? So now you can see that s squared, this s squared cancel. So you can see these two cancel. Cancel with this s squared. Okay, plus rs 1 over s partial v partial x minus rv. Okay, so let's cancel this stupid s. So cancel. Life is very difficult. Okay, so let me just clearly, and you can try to compute, but it's very easy. Just clear just some algebra. So after you treat, you get partial v partial tau partial v squared partial x squared plus 1 divided by -2r sigma squared minus 1 partial v partial x minus 2r divided by sigma squared v. Okay, so basically we clean it, so there's no ester. So everything become there's constant. Okay, so everything is constant. So in order to do this as a heat equation, we need to ignore this term, right? Because just remind you, right? So for heat equation usually is like ut equals to something uxx, right? So basically it's a heat equation. So we need to like remove some term, right? Probably there is some probably there is some nonlinear term are allowed, right? But this term partial v partial x should be ignored. Okay, so the trick is that we need to remove all this term and this term. Okay, so now that's the next step. So this is very standard. So let's write v. By the way, let me just try to change this. So let me just replace this tau to t, just for convenient. So forget about this previous shift. Okay, so now let's replace vxt to be exponential alpha x plus beta u times some function phi. So this is x and sorry, beta t. Okay, so it become vt just beta, right? Beta, just product beta, and v plus exponential alpha x plus beta t 5t. By the way, there's a phi here, right? So when you do the differentiation on beta, there's a beta out, so it become a phi u, so phi v, the same phi v, and then this is exponential the same and the phi t. Okay. Okay. Let's see. Okay, maybe let me just change your notation. Let me just change your notation to be this, just for the convenience. Okay, let me just write this as a exponential alpha x plus beta t and u of xt, because I wanted to be this, right? So and I call it phi u. So phi is exponential alpha x plus beta t. Okay, so when I do a derivative, then I get beta phi u plus phi of ut. Okay, and vx is alpha phi u plus phi ux. Now I can compute vxx. It's basically alpha squared phi u plus 2 alpha phi ux plus phi uxx. Okay, so this is simple. When you do a second derivative, you do a Leibniz rule again. Okay, so you can plug it in. Okay. Will plug it will be very cumbersome. But let's see. Maybe there's a chance. Okay, so let's right. So let's try to do this. Okay, so when I got this is the first term plus these 2r minus sigma divided by sigma squared minus 1 alpha phi u plus phi ux minus 2r divided by sigma squared v equals to beta phi u plus phi ut. Okay, so our goal is to make this ux term cancel, right? We want to first make this ux term cancel. So you can see that there's a way to cancel it. Okay. Okay. So let's see. So we want the least term and the least term cancel. Okay, so that means that our 2 alpha phi plus 2r divided by sigma squared minus 1 times phi needs to be 0. And is this correct? Yeah. So this will solve our alpha to be sigma squared divided by 2r divided by 2 sigma squared. Yeah. Looks okay. Okay, so this is our alpha choice. Okay, so once I choose this alpha, then I can ignore these two terms. Oh my god, so complicated. Okay, so now I still need to ignore this v term, right? So this v term in this case is u term. So I get beta phi u and this term. Okay, so I can choose beta phi u equals to 2r divided by sigma squared minus 1 alpha phi u. There's still a term alpha squared phi u. Oh, by the way, there's a still phi u here. Sorry. So there's a still minus. Yeah. So this term is also phi u, right? So it's minus 2r divided by sigma squared phi u. Okay, so this gives us a way to solve this beta. Okay, so yeah, and then you can solve beta. A little bit complicated, but yeah. Let's see. Yeah, so we can solve beta. But basically, you okay. So you know how I'm doing, right? So basically, you just do this and solve beta. Okay, so just after a TDS calculation, then we just write down the answer. Okay, basically, you can use this to solve beta. So after you can choose beta to be minus sigma squared plus 2r divided by 2 sigma squared. Okay, you can use this beta, then you can see a trick that there is a way to remove all this u term. So this every term cancel. So all this cancel. Okay, so if you get phi ut equals to phi uxx, so you can remove phi. Okay, so everything become like equation. Okay, so this is the answer that I think you can check this is true. Basically, just plug it in. Okay, so yeah, so this is our whole process. Okay, so let me just recall. Let me just talk about boundary condition, right? So in the beginning, that you will have some stock price, right? You have some boundary condition S, and then your V0t is basically 0, like for let's say t to t, right? And so after you do this, after you do the first time step, sorry, the first change of variable, that you got some interesting results, right? You got some your vx0 become f of exponential x, right? Because you change it to this exponential 1, and your t, right? Your t become like this. Okay. And in this case, that your original s need to be equal to 0, but in this case, your x, right, is basically it can be negative infinity to infinity, right? Because your s can be arbitrarily small when you take s to be exponential x. So x can be plus or minus infinity. Okay, and after the final results, after the final transformation, you get this. Now your x is negative infinity to negative infinity to infinity, and then your t is still t squared divided by 2 less than 0, and then your ux0 there will be exponential negative alpha x. Vx0 basically is negative alpha x fx exponential x. And yeah, so basically these are all final conditions. Okay, so yeah, so basically once you have this, then so you translate original this vector equation into this C equation once you do this change your variable. And the original s is square is 0, and then now it becomes He equation, so x can be negative infinity to infinity, and then 0 to t, and it becomes this. Okay, so once you have this, then you can solve the results using the He kernel. Okay, so probably we'll do next video. See you at next videos.